Look at the roof of this building and your brain will insist you're looking at something that shouldn't exist. A golden, 5-armed shape sprawled across the earth like a starfish someone dropped from orbit, so large that photographs genuinely struggle to communicate its scale, so strange that when it first appeared in aerial footage, people online argued about whether it was actually a spacecraft. It is not a spacecraft. It is an airport. And 5 years before that photograph was possible, this exact patch of land was a wheat field. No terminal, no roof, no runway, just farmland, quietly existing the way it had for generations, completely unaware that it had been chosen to become the largest single airport terminal building on the planet. That transformation happened in 4 years and 9 months, against a national deadline that could not move, could not slip, could not extend for any reason. And underneath the golden roof you're picturing right now, engineers were secretly solving a problem that had never been attempted at this scale in the history of construction. Building the world's biggest terminal directly on top of a live railway, running high-speed trains beneath the building, while the building itself was still being built above them. By the end of this, you're going to understand exactly how impossible that sounds on paper and exactly how a construction team made it real anyway. Along the way, you'll hear about a concrete floor that could crack itself apart with no load on it at all, a roof section that genuinely could not hold its own weight for months at a time, and one single connection point where, in a single moment, dozens of isolated pieces of steel that had existed separately for years suddenly became one unified structure for the first time. Before a single shovel of earth moved, the human side of this project had already begun, and it's the part almost nobody thinks to ask about. Roughly 20,000 people who lived on or near this land had to be relocated before construction could even start. And entire communities' worth of homes, farms, and daily routines uprooted and resettled to make room for a footprint large enough to eventually process 100 million passengers a year. That's not a footnote. That's the actual first chapter of this story, and it happened quietly, off camera, months before any of the dramatic engineering you're about to hear about ever began. Once the land was cleared, the deadline attached to it became impossible to ignore. This airport was tied to a major national anniversary, which meant the opening date was fixed the moment the project was approved, 4 years and 9 months out, with zero built-in flexibility for delays. You might assume that once the land is cleared and the date is set, construction is simply a matter of pouring concrete as fast as possible. The soil underneath this specific site made that assumption dangerous almost immediately. The first real problem engineers hit wasn't visible from the surface at all. It was underground, in the composition of the ground itself, which varied unevenly across the enormous footprint of the future terminal. Uneven ground means uneven settlement, and uneven settlement is quietly catastrophic for a building this size, because if one corner of a structure this massive sinks even slightly faster than the rest, the stress doesn't stay contained to that corner. It radiates upward through everything built on top of it, cracking floors, warping structural connections, and turning a survivable engineering tolerance into a building-wide failure. To fight this, dozens of pile-driving rigs ran simultaneously across the site, sinking deep foundation piles at a scale rarely attempted in a single continuous operation, each one verified, against exacting settlement calculations before the team trusted it to carry its share of the load. And then came a decision that shaped almost everything difficult about the rest of the project. Rather than build several separate terminal buildings the way most major airports do, engineers chose to build one single unified structure, one roof, one footprint, one continuous building large enough to be, on its own, the largest terminal on Earth. That single decision solved the problem of passenger connectivity beautifully. It also created nearly every structural and logistical nightmare that followed for the next 4 years. Because everything that would normally be distributed across multiple smaller independent buildings now had to work in perfect coordination inside one enormous continuous structure with zero room to isolate a mistake. Before the visible building could rise, 2 entire levels had to be constructed below ground first. And this wasn't a design preference. It was the only physically possible sequence given everything the site needed to accomplish simultaneously. Somewhere in those underground levels, a high-speed railway needed to run directly beneath the terminal, meaning the building's foundation design and the railway's construction had to be planned as one interlocking system rather than 2 separate projects stacked on top of each other. And almost immediately, the ground fought back. Groundwater at this site pushed upward against the excavation from day one, threatening to flood the underground levels before they could even be completed. And the response was almost brute force in its scale. Hundreds of dewatering wells running continuously, non-stop, for months, just to hold the water table back long enough for concrete to go in and cure properly. Nobody had solved a groundwater and foundation problem at exactly this scale before on a site this large, with a railway this critical running directly through the middle of it. Then came a problem that sounds almost absurd until you understand the physics behind it. The massive concrete floor slabs at the base of this building could crack themselves apart with zero external load pressing down on them at all. Concrete generates enormous internal stress simply as it cures and shrinks, and across a slab this size, that shrinkage stress alone was enough to fracture the structure before a single passenger, a single suitcase, or a single aircraft ever touched it. The solution engineers landed on sounds almost counterintuitive. They deliberately left gaps unfilled across large sections of the floor, sometimes for months at a stretch, on purpose. Fill those gaps too early, before the surrounding concrete had finished its natural shrinkage cycle, and the entire floor would crack from the pressure of its own curing process. The team also developed a specialized concrete mix engineered specifically to resist its own shrinkage tendencies from the inside, and layered a third defensive strategy on top of both of those, because on a project this size, no single solution was ever trusted alone. Every major structural risk got at least two independent backup strategies running in parallel, and for this particular problem, the team even borrowed a technique originally developed for earthquake-resistant construction and repurposed it to solve what was, on the surface, simply a concrete curing problem. It's a small detail, but it tells you everything about the mindset running through this entire project. Nothing here got solved with a single clever trick. Everything got solved with layered overlapping redundancy, because the deadline offered no time to discover a single point of failure the hard way. Above all of this ground-level chaos, the roof itself was quietly becoming the most technically demanding structure on the entire site. 8 massive curved columns were designed to carry the full weight of that enormous starfish-shaped roof, and remarkably, not one of those 8 columns stands straight to do it. Straight, conventional columns simply could not distribute the load the way this particular roof geometry demanded, so engineers designed columns that curve continuously along their height, which meant every single formwork panel used to shape those columns during construction had to be a unique shape. No repeatable mold, no shortcut, every curve poured individually to its own precise geometry. Inside those curves, rebar placement became a one-way decision with zero tolerance for error. Place a single reinforcing bar incorrectly inside a curved column like this, and it stays locked permanently inside the finished concrete. An unfixable mistake baked forever into a structural element holding up the roof of the world's largest terminal. Before a single structural beam for that roof was actually fabricated, engineers ran the design through 420 separate load scenarios: wind loading, snow, accumulation, seismic activity, extreme heat expansion, every combination the northern Chinese climate could realistically throw at this structure over its operational lifetime. The final roof design used 38 different beam sizes distributed across a network of roughly 170,000 individual structural members, and the engineering team deliberately optimized that design to save as much steel as possible, which sounds like good news for the budget and turned out to be a nightmare for fabrication, because minimizing material meant almost none of those 170,000 pieces were identical to each other. Every single one had to match its specific position on site perfectly, and the delivery sequence for all the 170,000 pieces had to match the installation sequence exactly, because getting that order wrong didn't just cause a delay. It stopped the entire assembly process dead, since building sections of this roof in the wrong sequence would let the earlier completed sections deform under their own weight before the rest of the structure existed to support them. The actual lifting of that roof happened in 26 separate individually calculated operations, starting with the very first section hoisted into place as a single complete piece, with 25 more lifts still to come after it. Every single crane position for every one of those 26 lifts was calculated individually in advance, because positioning a crane even slightly wrong at this scale doesn't just risk dropping a section, it risks twisting the entire partially assembled structure out of true before engineers even get the chance to correct it. 13 major sections of that roof were assembled piece by piece at full height, hundreds of feet in the air, with every single connection checked and verified before the crew was allowed to move on to the next one. Steel sensors monitored the structure 24 hours a day throughout the entire assembly process, and any unexpected movement, any reading outside the predicted range, triggered an immediate total pause across the site until engineers understood exactly what had caused it. There were 31 distinct moments across the project where 2 separately built sections of roof finally connected to each other, and every single one of those connections was timed against live, real-time deformation data rather than a fixed schedule, because the structure was still settling and shifting as it grew, and forcing a connection at the wrong moment could lock permanent stress into the frame. Temporary supports holding sections of the unfinished roof were removed slowly and deliberately, under constant monitoring, and if the structure showed any unexpected movement as a support came away, work stopped immediately, no exceptions. To understand exactly how the finished structure would behave if something went wrong, engineers built a scaled physical replica of the roof system, and deliberately shook it, simulating earthquake conditions just to watch it fail on purpose in a controlled setting. What they were specifically testing for was the difference between two very different kinds of structural failure. A gradual failure that gives warning signs over seconds, allowing time to react, versus a sudden collapse that offers no warning at all. The test confirmed which category this particular design fell into, and that answer shaped exactly how cautious the real-world assembly process needed to be, because at certain stages during construction, the partially completed steel structure genuinely could not hold itself up, remove its temporary support too early before the surrounding sections were locked into place, and the steel would deform permanently with no way to reverse the damage afterward. Finally, after years of piece-by-piece assembly, one single final connection joined the last two isolated sections of the roof frame together, and in that one moment, dozens of individually built pieces that had existed as separate, independently supported structures for months suddenly became one single unified roof, structurally whole for the first time. 2.5 years into the project, for the first time, the full starfish shape appeared visible from above, spanning up to 180 meters between structural supports in a single unbroken span, a deflection tolerance so precise it had to be calculated to exacting standards before anyone would trust weight to rest on it. With the steel frame finally complete, the glass could finally go on. Except almost none of the roof's glass panels turned out to be the same shape as each other, because the continuously curving geometry of the structure beneath them meant every panel needed to be individually fitted to its exact position. And then a problem appeared that nobody had fully anticipated during the design phase. This curved roof structure physically moves as much as 60 degrees in orientation-relevant expansion between winter and summer temperature extremes, a thermal shift that had to be accounted for in every single glass and steel connection across the entire span, or the panels would eventually crack or pop loose as the seasons changed. The skylights built into that roof weren't purely decorative or purely functional for lighting either. They were deliberately positioned to help guide passengers through the terminal intuitively, using natural light patterns instead of signage, so that a traveler moving through this enormous building could sense direction and orientation almost instinctively, without needing to read a single sign. From that central hub, 5 separate terminal arms extended outward, and each one of those arms independently repeated the exact same structural puzzle the central roof had just solved, essentially multiplying the engineering challenge by 5. 79 gate positions had to be fitted across those 5 arms simultaneously, a scheduling and logistics challenge significant enough to require its own dedicated project management structure completely separate from the main construction timeline. Somewhere in the design of this terminal, engineers made a decision nobody in commercial aviation had fully attempted before, stacking departures directly above arrivals within the same terminal structure, rather than separating them horizontally, the way most major airports do. That decision solved real problems in passenger flow and building footprint, but it also meant that kilometers of baggage conveyor belts had to be threaded through corridors and structural pathways that had already been locked into the design months before construction on those specific systems even began. Invisible infrastructure that never shows up in a single photograph of the finished building. But that had to be completed with total precision anyway. Standard fire and building codes typically cap maximum evacuation distance at 75 meters from any point in a building to the nearest exit. In a structure this vast, some interior points sat nearly 200 meters from the nearest natural exit route, which meant the code requirement simply couldn't be met through conventional layout alone. So engineers added 29 additional staircases, specifically to bring every point in the terminal back within safe evacuation range. Smoke behaves differently in a space this open and this tall than it does in a conventional building. And getting the airflow modeling wrong in a structure this size wouldn't just fail to meet code. It would make a real evacuation genuinely more dangerous. So smoke management became its own dedicated engineering discipline within the larger project. While all of that structural work continued, interior fit-out was happening across 4 separate levels of the building simultaneously, and at a certain point, the daily logistics of coordinating that many trades on that many levels inside one continuous structure became almost as complex as the structural engineering itself had been. In the middle of all that mechanical and structural complexity, the design team built real traditional Chinese gardens inside the sealed terminal environment, living landscaping integrated into a building whose primary job was processing tens of thousands of travelers an hour. Even the solar panel installations required custom mounting brackets in nearly every location across the roof, because almost nothing about this structure's geometry allowed for a standardized, repeatable solution. The curve that made the roof beautiful from above made nearly every fixture attached to it a unique engineering problem on its own. Over 2,000 individual lighting drivers were installed to automatically respond to changing daylight conditions throughout the day, all coordinated through a single centralized control system rather than operating independently. Facial recognition systems, automated baggage handling, and service robots were all integrated throughout the terminal, and none of those individual systems actually worked as intended until every single one of them could communicate reliably with all the others. A software and systems integration challenge running in parallel with, and arguably as demanding as, the physical construction itself. 293 separate mobility systems, escalators, elevators, and moving walkways were installed throughout the building, including one single moving walkway stretching more than 90 meters in a single continuous run, and every one of those, nearly 300 systems, required individual calibration and testing before it could be trusted with live passenger traffic. Roughly 98% of the materials and components used throughout construction were sourced domestically within China, which meant an enormous distributed supply chain had to move in exact lockstep with a single, immovable 4-year construction schedule. Outside the terminal building entirely, an entirely different engineering discipline was unfolding at the same time. 4 runways were being constructed simultaneously alongside the terminal structure, and this particular runway layout became the first in China specifically designed around actual optimal flight path geometry rather than simply fitting runways into whatever land happened to be available. Most people who fly regularly never think about what's actually underneath a runway, but a runway is never simply concrete poured directly onto graded earth. Beneath the visible surface sits a specific engineering danger that shapes almost every layer of the design. Standing water pooling on a runway surface can cause an aircraft to hydroplane during landing, a genuinely dangerous failure mode that runway drainage engineering exists specifically to prevent. With this facility designed to eventually handle roughly 300 takeoffs and landings every single hour at full capacity, the airport required what became the largest automated air traffic control system ever built for a single facility, coordinating aircraft movement at a density most airports never approach. Every single in-pavement runway light installed across the site had to be engineered to survive the direct weight of a landing aircraft rolling over it day after day, indefinitely, while maintaining an exact, precise beam angle that pilots rely on during low visibility approaches. Underneath the runway system itself, engineers built an actual tunnel specifically so that no ground service vehicle would ever need to physically cross an active aircraft path at surface level. Ausrichtiges, a detail almost no passenger will ever see or think about, existing purely to remove one specific category of ground collision risk before it could ever happen. Northern China's seasonal haze conditions made advanced low-visibility landing technology a non-negotiable requirement from the very first day of planning, not an optional upgrade added later. On May 13, 2019, exactly 4 years to the day after the original groundbreaking, the runway system was declared fully complete, and real aircraft finally touched down on runway calculations that had, until that exact moment, existed only as numbers on paper. But a runway alone doesn't make a functioning airport. Without completed cargo terminals and maintenance hangars, airlines still couldn't have actually operated real commercial departures from this site, no matter how finished the runway itself looked. Deep beneath all of it, the high-speed railway that had been under construction the entire time finally proved itself in the real world too, completing a 19-minute, 41-kilometer run that validated years of underground engineering work happening in near total secrecy directly beneath the visible construction site the whole time. Every layer beneath that finished runway surface had its own individual engineering purpose, stacked precisely on top of each other. 2,400 floodlights were installed across the apron area specifically, so ground crews could safely service aircraft in complete darkness without visibility gaps. Security checkpoints throughout the terminal were designed from day one for an eventual capacity of 100 million passengers a year, engineered for that. Future scale, even though opening day volume would be a fraction of it. At peak construction, up to 50,000 workers were on site simultaneously, coordinating across a footprint this enormous, and across the full 5 years of construction, the project reported 0 recorded production safety. Accidents, a statistic that, on a project moving under this much deadline pressure at this scale, simply does not happen by accident. It happens through relentless, continuous safety enforcement applied to every single shift, without exception. Across the life of the project, engineers and construction teams ultimately developed 65 entirely new construction methods and techniques because the existing global engineering playbook simply had no established answer for several of the specific problems this site presented. 10 test passengers moving smoothly through a checkpoint proves almost nothing about whether that same checkpoint can handle hundreds of real travelers per minute under actual operational pressure, and testing, specifically for that gap between small-scale simulation and full-scale reality, became its own dedicated phase of pre-opening preparation. The final challenge wasn't structural at all, it was organizational. 2 enormous, technically separate projects, the terminal complex and the runway and airfield system, had to be integrated and made to function as a single unified airport before opening day. The airport's actual name wasn't finalized until roughly a year before it opened, and by that point, some of the hardest remaining months of the entire project were still directly ahead. Airline officials had to determine exactly which carriers would relocate to this new facility and which would remain at the city's older, established airport, a decision process that ran in parallel with construction, straight through to the very end. Slowly, section by section, construction barriers around the finished portions of the terminal started coming down, and for the first time in nearly 5 years, walking through the space actually felt like walking through a functioning airport rather than a construction site. That period became the last realistic opportunity to catch any remaining problem before an international opening ceremony would put the entire finished building in front of the world. The apron's 2,400 floodlights clicked on, ready for ground crews to work safely around aircraft at night. Every security checkpoint, engineered from the beginning for an eventual 100 million annual passengers, had to work correctly on day one, at a fraction of that eventual load, with zero room for early failures. Somewhere in that final stretch, nearly 5 years of continuous construction crossed one invisible line, and the site simply, quietly became an airport rather than a project. This became the first hub airport anywhere to commit entirely to new energy ground vehicles across its full operational fleet. Every tug, every truck, every bus moving passengers and cargo across the tarmac running on something other than traditional fuel from opening day forward. 28 surrounding cities were connected to the new facility within a 3-hour rail radius, a scale of regional integration built deliberately from the start, designed to make this airport function as something considerably larger than a single building. On September 25th, 2019, the first commercial departure lifted off from land that had been open farmland exactly 5 years earlier. An aircraft climbing away from a runway that, within living memory of the workers who built it, had been wheat fields. On that same day, the city's oldest airport closed its doors permanently, one era of aviation history ending in the same 24 hours that a new one began. Seen from above, the finished building genuinely does look like a golden starfish resting on the landscape, or, depending on the angle and the light, something closer to an alien spacecraft that happened to land in northern China. Both descriptions somehow fit equally well. What almost nobody watching that footage today ever sees is what this exact patch of ground looked like 18 months earlier. Scaffolding, exposed rebar, stress sensors wired into curved steel columns, engineers staring at deformation readouts under floodlights at 2 a.m, wondering whether the next support removal would hold. All of that tension, all of that risk, all of those years of layered contingency planning against a deadline that could not move are completely invisible now. What's left is simply a golden roof catching the light, quietly beautiful, and almost nobody looking up at it has any idea what it actually took to make it look that easy. Set this project next to almost any other major airport built in the last few decades, and the comparison starts to feel unfair in a very specific way. Most large international airports are built as clusters of separate terminal buildings, connected by trains or long walkways, precisely because splitting the structure into smaller, independent pieces makes each individual engineering problem more manageable. You can isolate a mistake, adjust one building without redesigning the whole site, and avoid the exact kind of cascading structural risk that comes from putting everything under one continuous roof. This airport deliberately rejected that safer path. One building, one roof, one integrated structure large enough to be the biggest terminal on the planet, built on a 4-year deadline that offered no room to discover a design flaw the hard way. That decision is the quiet thread running underneath every single engineering story in this video. The uneven soil, the self-cracking concrete, the curved columns, the roof section that couldn't support its own weight, the 60-degree seasonal movement in the glass, none of those problems exist in isolation. Nearly all of them trace back to the single choice to build one unified structure instead of several separate ones, which means every solution the team found had to work in concert with every other solution all at once, with almost no tolerance for anything going wrong in isolation. And underneath all of the numbers, the 420 load scenarios, the 170,000 structural members, the 26 roof lifts, the 60, 5 newly invented construction techniques, it's a simpler fact that's easy to lose in the scale of it all. 20,000 people gave up their homes so this could exist. 50,000 workers at peak spent years of their lives inside a construction schedule with zero flexibility on a site where a single miscalculated crane lift or a single misplaced rebar tie could not be undone. And across 5 years of that pressure, on a project this enormous, this technically unprecedented, this deadline locked, the recorded safety outcome was 0 accidents. That number, more than the golden roof or the starfish shape or the record-setting terminal size, might be the single most extraordinary statistic in this entire story. because it means somewhere underneath every dramatic engineering decision documented here, there was an equally relentless, mostly invisible commitment to making sure everyone who built it got to walk away from it,